Okay, you can start whenever you.
So let's continue our session. The next speaker is Jussi Behrndt. The title is Spectral Shift Functions and Dirichlet-to-Neumann Maps. Please.
Yeah, thank you very much for the introduction. And yeah, many thanks to the organizers of this online conference for inviting me to speak here. This is a great opportunity to meet a number of colleagues online. Well, the talk is about spectral shift functions and a particular, in our opinion, new representation of these interesting objects. It's joint work with Fritz Gestesi from Baylor University in Waco and Shu Nakamura, who is now at Gakushūin University in Tokyo. So the talk actually consists of 3 parts. The first part is a kind of introduction, a very brief introduction, I should say, to the concept of the spectral shift function. The second part of the lecture contains the, let's say, main abstract result, where we provide a representation of the spectral shift via a certain object that you could call abstract Dirichlet-to-Neumann map, or that is actually called in extension theory Weyl function or Titchmarsh Weyl function. And the third part of this lecture is about a couple of applications where you can see concrete examples from PDE problems to express a spectral shift function with our abstract formula and representation. All right, so let's move to the introductory part, which is actually a very, very brief history of the spectral shift function. And in this context, I should refer to the standard monograph is in this theory, which are by Dimaya 5, very well known monographs on mathematical scattering theory. Yeah, I was of course hoping that Dima would be present for this talk. Well, he will be missed. It's it's very sad actually. Faye's books, nevertheless, of course, will remain and will be used by experts and specialists in mathematical physics. And well, they serve as an excellent source on more information on the spectral shift function. Apart from Dima's books, I would also like to point out 2 survey papers, one by Dima and Behrmann from '92, and a slightly more recent survey paper by Behrmann and Alex Pushnitsky on the spectral shift functions. And these also serve as a nice and, of course, more condensed overview of the notion of spectral shift. So what's the situation and what it is about? First of all, our general assumption for this lecture will be that H is a Hilbert space. We are working here with self-adjoint operators in our space H, A and B, and typically these operators you should think of as unbounded. Well, in this context, the spectral shift function probably appeared first in the physics literature, introduced on a more formal and heuristic level by Lifshitz in 1952, who made the following assumption. If a B minus A is finite rank, so B is a finite rank perturbation of A, then Lifshitz claims there is a real valued function psi, such that the trace formula that you can see on the bottom of this slide holds. So you form phi of B, let's say via functional calculus for self-adjoint operators, and you form phi of A. These will probably remain self-adjoint or at least closed operators with non-empty resolvent set. You build their difference, and if this difference is trace class, then actually it admits an integral representation using the derivative of phi and this real-valued function psi, which is called spectral shift function in this context. Well, Lifshitz paper is on a more heuristic and physical level, and this is more like a formal derivation of this formula. It's not precise in the sense that the classes of functions phi and so on are not specified for which this type of trace formula holds. So it didn't take long until it became more rigorous, and this is also why the spectral shift is often referred to Krein's spectral shift function. So the two main contributions by Krein from 53 and 62 made this concept of spectral shift actually rigorous. First of all, Krein went beyond finite rank perturbations, and he actually assumes in his first attempt that the difference of our self-adjoint operators B and A is trace class. To be a bit more precise, you probably want to take the closure of the difference. And so the difference admits a continuous extension to a trace class operator. So under this assumption, Krein proved the following remarkable formula. So there is a real valued function psi integrable such that the trace of the resolvent difference can be expressed in this type of integral expression. So psi of t you can see in the numerator, and in the denominator is t minus lambda squared. So if B minus A is actually trace class, then also the resolvent difference is trace class. In addition, this function psi has satisfies this condition. So the L1 or the integral of psi is actually equal to trace B minus A. In a way, this is what you would expect from the earlier Lifshitz formula. Let's go back here. You see, if in this Lifshitz trace formula you plug in the function phi equal to t, then actually this gives you trace of B minus A on the left-hand side, and the derivative would be equal to 1. So you get trace B minus A is equal to the integral of psi of t dt. This is what Krein made rigorous as well. Now the trace formula of Krein plate formula can of course be converted in the Lifshitz formula by just using the special function phi of t being equal to 1 over t minus lambda. So this formula of Krein is basically a special case of these more general trace formulas you just have seen. Krein was also worried for which classes of functions phi beyond 1 over t minus lambda this formula actually remains valid, and he extended it to the so-called Wiener class, functions phi where the derivative admits an integral representation, as you can see here, using a complex Borel measure sigma. Well, spectral shift, so why shift, let's say? Here's a corollary that you can derive from this more general theorem. Consider an interval, an open interval AB, where also the closure is actually contained, or well, has empty intersection with the essential spectrum of A. So you are basically in a spectral gap, still allowing discrete eigenvalues of finite multiplicity inside delta, and the endpoints of delta as well should not belong to the band of continuous spectrum of A. Well, in that case, the trace formula above, or the Lifshitz trace formula, leads the following formula at the bottom. So the difference of the spectral shift at B and at A, where you take the limit from the left at B and the limit from the right at A, is actually equal to the difference of the dimension of the spectral projections of B and A corresponding to the interval delta. So this formally follows by just using the indicator function of this interval delta and plugging it into the Lifshitz trace formula. you can make this rigorous, and the outcome is actually this corollary. So kind of the spectral shift, if you compare its values and at A and at B, it kind of tells you how much change there is in that case here inside the discrete spectrum in a gap of the essential spectrum. So Krein went on. Not surprisingly, you can extend this business to the unit circle by considering unitary operators U and V under the same trace class assumption as he had for self-adjoint ones. Anyway, if you have it for unitary operators, then via Cayley transforms, you get a step further and you consider resolvents, which of course is more general and in a sense more appropriate. So suppose again that B and A are self-adjoint operators, and assume that the resolvent difference is a trace class operator. This again is more general than just assuming that the difference of the operators themselves is trace class, because these operators are unbounded, and so resolvent comparability is let's say the more natural and appropriate way to formulate conditions. So if you have trace class of the resolvent difference, then actually the spectral shift may not be L1, but still locally L1, real valued function, which satisfies a certain integrability condition that you can see here, such that the trace formula for the resolvent difference holds in the same way as you have seen it in the previous result by Krein. This function psi here is not necessarily unique because you are just in the L1 log class, but it remains unique up to a real constant. So again, the trace formula is satisfied for the function phi being equal to 1 over t minus lambda inverse, but you may also go to higher powers of resolvents, which means you plug in phi is 1 over t minus lambda to the power minus k for some non-negative integer k. So there was a lot of interest in extending trace formulas to large classes of functions, and maybe the most remarkable results and those that went or cover the largest classes of functions are by Vladimir Pella, and I'm here just referring to one of his many contributions from 1985. In this context, let me also show you how the spectral shift function appears in scattering theory. And by this, I mean the connection of the spectral shift with the so-called scattering matrix via the Biermann-Krein formula. So the scattering matrix is basically a unitary copy of the scattering operator, which is built of the wave operators in case they exist and they are complete. So suppose you have a complete scattering pair, two operators A, B, where the resolvent difference is trace class. Then there's a scattering matrix, and this scattering matrix, actually its determinant, is directly connected with the spectral shift function that appears here as a phase. So the determinant of the scattering matrix is equal to the exponential of minus 2 pi I psi of lambda, where psi is the spectral shift. So this is a remarkable and interesting formula which connects the spectral shift with more objects from scattering theory. So now let's go beyond the assumptions Krein had on top of this slide. So let's try to go beyond trace class resolvent difference. And the first substantial and most remarkable result in this context is from Koplienko from 71, who did not assume that the resolvent difference is trace class, but who just assumed that the resolvent power difference for some positive integer m is trace class. This is intuitively believed as a weaker condition than the trace class condition itself. But let me emphasize here a small item. You see, Koplienko has to assume in the general case that there is a spectral gap. So the point lambda that appears here in the resolvent power difference is assumed to be a point which is real and belongs to the resolvent set of both operators. Of course, for semi-bounded ones, this would be no difficulty, but in the general case, it's a slight restriction. Anyway, he gets a trace formula and a spectral shift psi, which is locally L1, for the m's power resolvent difference exactly as you expected. So the psi of t again appears here in the denominator, and phi, the function phi that is being used here is of course 1 over t minus lambda to the power m. And then you see its derivative here in the integrand. Well, then it took a long time until one further deep contribution in this context appeared. And now this is again Dimaya 5 from 2005, where he actually was able to relax Koplienko's condition in the case that he's considering odd resolvent power differences. So if that's the case, you do not need to assume that there's a spectral gap and you get the same spectral shift as Koplienko got, and with the same integrability condition, and of course with the same trace formula. So once again, it's just a nuance, but an important one. So Dimaya 5 was able to remove the condition that there's a real point in the spectrum when considering odd resolvent differences. So far, a brief introduction to the spectral shift. And now here, an incomplete but still a list of many colleagues and scientists contributing in the context of spectral shift. So I'm not going through all these contributions, of course. Let me just mention maybe the papers by Krein and Yavrian, who got the spectral shift representation for certain finite rank cases. The paper by Fritz Gestesi and Simon, where the so-called Xi function was used to express the spectral shift, and a paper by Alex Pushnitsky, where a different representation for the spectral shift was found. And well, as you can see, a huge number of contributions in context of the spectral shift, which has been computed or analyzed in more specialized and particular situations. So now let me jump to the second part of the talk, which will actually contain the main abstract result. So this is a representation formula for the spectral shift function via the Weyl function. Good. For this, we jump into abstract extension theory of symmetric operators in Hilbert spaces. So from now on, imagine S is a densely defined closed symmetric operator, and to keep it interesting and non-trivial, assume it has infinite defect. By this, I mean that there is a self-adjoint extension, but it's an infinite dimensional extension. So S is a kind of small symmetric operator. This is a typical case in PDE applications. For such a symmetric operator, I would like to define a certain notion of boundary triples, which we call quasi-boundary triple. And such a quasi-boundary triple, it consists of an auxiliary Hilbert space G. This is also referred to as boundary Hilbert space, and an auxiliary or an additional operator T, which is in general not equal to the adjoint S star, but its closure is. So T, in short, is a core of the adjoint S star. This T is typically not unique. You can choose any T that has this core property. Then a boundary triple of this form has two boundary mappings. Think of Dirichlet-to-Neumann trace. These trace or boundary mappings are defined on the domain of this core operator T. They map into this boundary Hilbert space G and satisfy a number of conditions. The probably most important one, if one wants to rank them, is this abstract second Green's identity, where on the left-hand side, you basically do integration on your domain. And on the right-hand side, if gamma 1 and gamma 0 are trace maps, Dirichlet-to-Neumann, you have L2 inner products on the boundary of your domain. And this formula then naturally holds in this context. Next is a kind of maximality condition. This boundary space G should not be too big. Not too big in the sense that the range of the vector map gamma 0, gamma 1, now again defined on the domain of the core operator T into the Cartesian product of G with itself. This should have dense range. And then there is another maximality condition, which kind of tells you that if you restrict T by your first boundary condition, let's say Neumann or Dirichlet, then actually the operator you end up with is supposed to be self-adjoint. So this A naught defined here is naturally a symmetric operator. This follows from the abstract Green's identity. But in general, it's not self-adjoint, and one needs to require this. If one works with so-called standard or ordinary boundary triples, this third condition is always satisfied. But in the more generalized case we are looking at here, one actually has to put it and require it in the definition. So this looks very abstract, but I hope I can convince you that it's a natural type of definition and notion. So think of a Schrödinger operator minus Laplacian plus V. Keep things simple. So let's say omega is a domain which is somewhat smooth. So its boundary is assumed to be C2. And the potential V is a kind of good and mild perturbation. So let's say it's L infinity function real. If you work with such type of differential expression, you may assign operators to it that fit into the above definition as follows. So our underlying closed symmetric operator is the minimal operator minus Laplacian plus V, now defined on functions from the Sobolev space H2, where we actually require Dirichlet and Neumann trace both vanish. So this operator intuitively is a small operator. Its domain is H2 0, you could say. This is far from self-adjoint. It's only symmetric. So S star, its adjoint in this case, is again the same differential expression, but now acting on the maximal domain in L2. So it acts on L2 functions f in a distributional sense, such that the distribution Laplacian f, or Laplacian f plus v, if you wish, is again L2. So this is really a big set of functions, and it is remarkable and important to observe here that this set is not contained in any Sobolev space with a positive regularity. So this is not H2, it's bigger. So you do not just lose boundary conditions when taking the adjoint, but you also lose regularity. This is a big difference to the case of intervals and ordinary differential operators. So in the PDE case, life is a little bit more subtle. Anyway, now there is a T which serves as a core operator, and here a convenient choice could be, it does not have to be, but it could be the differential expression minus Laplacian plus V, now actually restricted onto the natural Sobolev space H2 omega. In that case, one can verify the closure of T is indeed the maximal operator S star. Well, this is classical. Green's identity here is just satisfied with integrals on the domain omega on the left and boundary integrals on the right. So you can just read off one possible choice for such a quasi-boundary triple, which here would be as auxiliary Hilbert space G. You take L2 on the boundary, and your boundary maps could be gamma naught being the Neumann trace, and gamma 1 could be the Dirichlet trace. So the choice of the maps is not unique, but this is the one I will be using later on as well. Okay, so long story short, such a quasi-boundary triple appears naturally if you do extension theory for Laplacians or Schrödinger operators on domains with boundaries. And here is one possible choice how you may do that. Good. So besides boundary maps, there is more abstract analytic notions associated to such a quasi-boundary triple, and these are the so-called gamma field and Weil function that I would like to introduce now. So again, we are on the abstract level. We have a quasi-boundary triple for a symmetric operator S with a core operator T, where the closure is equal to S star. And now we consider the, let's say, solution space or deficiency space, which is the kernel of T minus lambda. We fix lambda off the real line for the moment, and we define operators gamma lambda and m lambda that do the following. Gamma lambda is actually a map from the boundary space back into your original Hilbert space H. And what it does is it is just the inverse of your first boundary map gamma naught. It's actually well defined here because you are working off the real line and you just work with solutions or kernel elements of T minus lambda. So gamma lambda basically maps from the boundary back to the domain. And M of lambda does a little bit more. It does the same job as gamma. It first takes a gamma naught F lambda, and then you apply the second boundary map to that F lambda solution actually, and then formally you map from the boundary space into the boundary space. This you can do at least for any lambda of the real line. And in this way, these objects become operator valued functions called the gamma field and the while function. Let's look at the examples, what's going on. So basically the gamma is a kind of Poisson operator, which solves a boundary value in PDE problems. M of lambda assigns in applications Dirichlet traces of solutions to Neumann traces or vice versa. So M of lambda in PDE is typically something like Dirichlet-to-Neumann or Neumann to Dirichlet map. You may also, by playing with boundary maps, view this as Neumann to Robin or Robin to Dirichlet and so on and so on. There's many choices. In our particular example we have just seen, the situation is the following. First of all, the kernel of T minus lambda, where actually gamma field and while function operate on, is nothing else than the space of H2 solutions of the differential equation minus Laplacian f plus Vf is equal to lambda f. Lambda, of course, non-real. This has a unique solution. And what the gamma field is now doing is actually it takes this solution and or the trace of this solution and maps it to f of lambda, which here, because gamma naught is the Neumann trace, means that gamma lambda takes a boundary element phi. In the present situation, it is a function with h1/2 regularity. It takes a boundary element phi and it assigns to this boundary value a solution of the corresponding PDE at the spectral value lambda, where the corresponding Neumann trace is equal to the phi. This is the standard property of a Poisson operator in PDE theory. So what does M of lambda do? It goes just a step further. It takes this phi, which is the Neumann trace of a solution, and it assigns to this Neumann trace the Dirichlet trace of the solution. So actually here, the Dirichlet trace, it is viewed as an object in L2, but of course we know it has beta regularity. So it's actually in H3/2. So in our example, M of lambda is a Neumann to Dirichlet map. Good. Now we again return to abstract theory. So we look at quasi-boundary triples and how they can be used in perturbation problems. And this is what makes these objects quite convenient. Now, coming back to our initial situation, we have two self-adjoint operators, A and B, acting in the same Hilbert space. We consider the intersection of the two operators in the sense of graphs. In general, this intersection could be very small, but let us assume here for the moment that this intersection is actually a densely defined operator. So the key assumption here, it could be relaxed, but then it leads to linear relations, which I would like to avoid here. The key assumption here is that the intersection of the domains of A and B, where actually the actions of A and B coincide, this set, which we call here domain of S, is dense in our original Hilbert space. And we then define our operator S on this small set, basically, as the action of A, which is the same as the action of B. So in short, it's what is just said here on the first line. S is the intersection of the graphs of A and B. So it's a kind of underlying symmetry, and of course A and B can both be viewed as self-adjoint extensions of S. So this is how quasi-boundary triples now come into play. So in this situation, you can construct a core operator T, which is a core of the adjoint, and you can construct an auxiliary Hilbert space and trace or boundary maps gamma naught and gamma 1, such that actually our operator A corresponds to the kernel, or its domain, let's say, corresponds to the kernel of the first boundary map, and our second operator B corresponds to the restriction of T to the kernel of the second boundary map. So in an abstract level, you could regard A as kind of Neumann and B as Dirichlet, basically. And we took any two operators and put them in the scheme. Now you use quasi-boundary triple standard theory and you observe that the resolvent difference of A and B can be factorized in a very convenient way. So this is where the gamma field and the Weil function actually appear. Well, the resolvent difference on the left-hand side is, well, actually acting on your initial domain omega, let's say. And a gamma lambda star takes you from omega to the boundary. This is where m lambda inverse, the Weil function, acts. And then with gamma lambda, you basically come back to the original domain. So in a way, in this formula, you kind of localize the perturbation or the difference of A and B or their resolvents. You basically localize this in the boundary or in the auxiliary Hilbert space G, which serves as boundary space. So this is a convenient observation, and it comes from abstract extension theory. Well, with this lemma in mind, we are now ready to formulate our main result in a good, or let's say special case, which is first order, and you shall see why in a second. So we have two self-adjoint operators, A and B, and we assume that their intersection S is a density-defined operator, and we choose a quasi-boundary triple just in the way as you have seen it in the previous lemma. So A and B actually correspond to the restrictions of the core operator T to the kernels of the boundary maps gamma naught and gamma 1. Then there's a type of sign condition, which I will explain a little later. So let's assume that there is an ordering of the resolvents. So for some real point mu, which belongs to both resolvent sets, of course, you have to assume that there is a gap. You have this inequality between the resolvents of A and B. Now we put some additional conditions on the objects that appear with this quasi-boundary triple. So the first thing is this gamma field or this gamma mapping, at some point lambda naught should be a Hilbert-Schmidt operator. Well, its closure to be more precise. And I would also like to have the Weil function and its inverse to be bounded operators, not necessarily everywhere defined and closed, but to be bounded operators for some values lambda 1 and lambda 2 of the real line. Well, in that case, we have seen this formula already, but now it gets a little bit better. You see, if you look at the right-hand side, gamma lambda is Hilbert-Schmidt actually everywhere. The same is true for the adjoint. So you have two Hilbert-Schmidt operators on the right-hand side. The inverse is bounded, so no surprise, this will become trace class. So under these abstract assumptions on the gamma field and M function, the resolvent difference of A and B becomes trace class. And so we may ask for the existence of a spectral shift. And this is the first technical, but it's a key observation. Under these conditions, you can prove that the M function, the Weil function, or its closure, you can form the logarithm of this closure, which is again an operator in your auxiliary Hilbert space G. And then one can show that the imaginary part of this logarithm is a trace class operator. This is done naturally on the set of lambdas where this object is defined, which is now just all lambdas of the real line. Anyway, if you have a trace class valued function in this particular setting, then there is results by Nabokov and others that ensure that it admits limits when your parameter lambda approaches the real line. And these limits, and actually their trace, lead to a spectral shift function for the pair AB. So what's done here is you take the imaginary part of the logarithm of m of lambda for lambda in the upper half plane. Then you can conclude that the limit, or this is trace class, this we have seen already, and you can actually conclude that the limit exists in the trace class topology if you send lambda to the real line, almost everywhere. And this gives you, well, up to the factor 1 over pi, a function psi which serves as a spectral shift. So in particular, it gives you the trace formula that we have seen before. So this is a very abstract type result. In a nutshell, it tells you you have two operators which can be viewed as self-adjoint extensions of a symmetry. Under some additional conditions on the QBT that appears and the quasi-boundary triple, the resolvent difference actually becomes trace class, and out of the Weil function, we can give an explicit formula for the spectral shift function of this pair. Now, why is this a first order case? Well, it's first order because we compare resolvents instead of resolvent powers. So the resolvents appear here in first order. Let's go a step further, which is now called the higher order case. It becomes a bit more technical. The starting point is the same. We have two self-adjoint operators. We have a symmetry. We fix a quasi-boundary triple. And we require a sign condition. We want M inverse and M to be bounded for certain values of lambda1 and lambda2. And this looks technical, but that's just how it is. You have to impose a number of trace class conditions on derivatives of products of the gamma field and of M inverse times gamma star. So all these conditions are actually really needed, and you shall see, or we shall see in a number of applications later, that actually they are met. So this is a set of technical trace class conditions, but they ensure the following. If these all SP conditions are satisfied, then actually it's not the resolvent difference, but the resolvent power difference of order 2k plus 1, which becomes trace class. And in that case, one can still show a weak variant of the previous formula, which gives you a spectral shift function expressed as the limits of the imaginary part of the logarithm of the closure of the M function. And now this in the weak sense, because we have here fixed an orthonormal basis phi j in our auxiliary boundary space G. With this spectral shift, again, we have trace formulas as Krein, Koplienko, and Yafayev supposed to have in the case or in their exploration of the spectral shift. Okay, some remarks are maybe appropriate at that point. So we had a sign condition, which for the case of semi-bounded operators just tells you that A is less or equal to B. This is very much in accordance with the spectral shift, because as it is constructed here, it's naturally non-negative. And this actually reflects ordering of operators as well. Well, I mentioned it briefly, but you see the technical key difficulty is to work with this logarithm of the M function and to prove that it has in the limit, it has a trace class property to the real line. So by logarithm, I'm actually mean here the cut of the logarithm along the negative imaginary axis. This leads to an integral representation, as you can see here, and it actually serves as the definition of the logarithm of a dissipative operator. And well, you need to extend certain integral representations of Ries-Herglotz type to actually prove that then Nabucco results on trace class limits actually can be applied. Okay, more remarks. The last one is just about analysis of resolvent power differences for elliptic PDOs. This is a long story. It goes back to Biermann. And one paper I would like to mention in this context is with Langer and Lotorajczyk, where this has been done in an abstract and very detailed level. So the representation of the spectral shift via the Weil function is not entirely new. You can find it for rank 1 perturbations. So instead of trace class or trace class power differences, rank 1 in the ordinary sense. There's a paper by Heinz Langer, Henk de Snoo and Javrian from 2001, where this has been done, where the expression is done with the so-called Q function. For finite rank perturbations and first order case, so resolvent difference, not power difference, we had it with Mark Malamud and Hagen-Neidhardt in a paper of 2008. There are other representations by Malamud and Neidhardt using the modified perturbation determinant for the spectral shift, or in the context of the spectral shift and the M function. And then I should also mention that the scattering matrix can also be expressed with the M function that you have met here. And this is something that has been done for a long time. The first contributors here are probably Adam, Jan, and Pavlov, who did it in the finite rank case. And it was then extended to trace class perturbations by Malamud, Neidhardt, and myself. And there's also an interesting paper by Mantile, Posilicano, and Cini, where a very similar formula is derived. Okay, now this was a lot of abstract operator theory and, well, some technical conditions. Let's see how it can be applied, if at all. So here's my first application. Robin boundary conditions, actually different Robin boundary conditions. So we are back in the case that our operators are Schrödinger minus Laplacian plus real potential. And they are now defined on H2, and we consider Robin boundary conditions where, yeah, now I should go slowly maybe. So omega is a domain in the n-dimensional Euclidean space. To make life simple, suppose this domain is compact and it has a smooth boundary. The potential V is real, and the coefficients appearing in the Robin condition are assumed to be real-valued function, C2 to have sufficient operator domain regularity, and to make it non-trivial, we assume that beta naught and beta 1 are not identically equal. There is an X where the two differ, so the operators should differ. We shall be working with the Neumann to Dirichlet maps that we have met before. So it just maps Neumann traces of solutions to Dirichlet traces, and we view this object n of lambda actually as an operator in the L2 space on the boundary. So here's the result. If k is a non-negative integer, which is larger or equal to space dimension -3/4, then actually the 2k plus first order resolvent power difference of these two Robin Laplacians, self-adjoint Robin Laplacians, I should add, this resolvent power difference becomes trace class. This is just by, well, you construct a quasi-boundary triple and you verify all the abstract conditions in this case, and that gives you the trace class condition for the difference here. Then you can express the spectral shift using our abstract formulas, and it comes now again, as you expect, with the imaginary part of logarithms of certain functions, and these functions script m0 and script m1 are actually built out of the Neumann to Dirichlet map that you have just above the theorem. So you use the Neumann to Dirichlet map and you use the functions beta I, and you use an upper bound beta, which is a real number, just a majorizing beta naught and beta 1. And you can actually verify that these inverses and all these objects here make sense in terms of wow. There was a problem here, but I hope you can still hear me. So there's M0 and M1, as I mentioned, and these two operator functions appear here in the imaginary parts of the logarithms. And this is a weak representation, again, because we need to use an orthonormal basis in the L2 function on the boundary made of the phi j's. So the case gets a little better if we go in space dimension 2 and 3. So why is that? So if you look at the assumptions of the theorem, then you can see that for k equal to 0, they are satisfied as long as n is equal to 2 or to 3. So if that's the case, the resolvent difference and not the higher power difference becomes trace class, and we get a nice and explicit representation for the spectral shift, not using an orthonormal basis, but really in the terms of operator limits. Good. Next step is here, example number 2. Compactly supported potentials in Euclidean space. I'm going the wrong way, sorry. And by that, I have the following in mind. Our unperturbed operator A is just minus the Laplacian, and our perturbed operator B is Laplacian perturbed by the potential V, where actually V is assumed to be a real valued potential which is compactly supported. Both operators are self-adjoint in L2 Rn if you define them on H2. This is clear. Now we do a so-called multidimensional Glassman splitting, which means that actually I'm picking a kind of big ball, B plus, let's say, which is sufficiently large and contains the support of our potential V. Now I would like to go in 3 steps. The unperturbed operator A, which is just the Laplacian, I would like to first compare with the direct orthogonal sum of A plus and C. So A plus is actually the Dirichlet Laplacian in the L2 space of the ball B plus, and C is the Dirichlet Laplacian on the exterior ball, on the complement of the ball, defined on H2 with Dirichlet boundary conditions. So there's no potential in the first pair. Then in the second step, we compare the orthogonal sum of A plus and C with B plus and C, where B plus is now perturbed on the finite domain on the ball B plus by the additive potential. Here, as you can see in the second pair, the right lower component is not changing, but the perturbation is in the upper left component. All these objects here have compact resolvents due to the finite domain. And in the last step, we compare B plus C with our, well, actually full perturbed operator B. So the multidimensional Glassman splitting is basically via the sphere of a ball B plus, which contains the support of V. This is a standard technique. And the spectral shift function for the operators A bar plus and B plus, which actually live on this finite ball and have compact resolvents, this spectral shift function is just the difference of the counting functions of the eigenvalues, because here they just appear eigenvalues of finite multiplicity. Good. So now, this can be more abstract, but let's go to the spectral shift function of the full pair. So again, if there is a positive or non-negative integer k, which is related to space, or which is larger than space dimension minus 2/4, then the 2k plus first powers of the resolvent differences become trace class, now in the L2 space of Rn. And the spectral shift for this pair AB can be written as a sum of, let's say, 3 spectral shift functions. The last term, psi plus, is the spectral shift of the operators on the finite domain, which, as I mentioned, is just the difference of the eigenvalue counting functions. And the other 2 items, script n and script nv, well, they are made out of Dirichlet-to-Neumann maps of the interior or the exterior PDE problem. So D plus D minus stands for Dirichlet-to-Neumann map corresponding to the Laplacian at minus lambda. And then the index V corresponds to the Dirichlet-to-Neumann map of the Laplacian with inside the ball where the potential V is actually present. So the iotas and the iota tildes are just technical things that help you keep you in the right spaces and are of not deeper interest here. So we get a spectral shift for this particular case using a three-step method and a type of Glassman decomposition. Just one remark, you see the spectral shift of the interior pair is just a counting function. It's a step function. And it's far from continuous, of course, but the full thing regarding the complete problem on the full Euclidean space, one can verify it here, but it is also known from previous results on scattering theory with compactly supported potentials. The psi itself is continuous. And this is a remarkable fact which you cannot immediately expect from the formula above. Good. Then there is a third example. I would like to spend a few more minutes on that one. It goes beyond the first 2 examples in a way, and it's dealing here with so-called singular potentials or delta potentials supported in hypersurfaces. So in a similar case as in the multidimensional Glassman splitting we just saw, think of omega plus being a bounded domain, smooth boundary, and this boundary is denoted by C, and the complement of omega plus, or its closure, is actually an exterior domain which is unbounded and is denoted by omega minus. Both omega plus and omega minus have the same boundary C, which is a compact closed manifold in n-dimensional Euclidean space. We have a real valued potential V from L infinity, and we have coefficients that will appear in front of the singular perturbation, alpha or alpha inverse, which are assumed to be real valued L infinity functions on the hypersurface C. Now we want to consider the pair A delta alpha compared with the free operator, which does not feel the hypersurface or any singular perturbation. So A is just minus Laplacian plus potential, and A delta is actually formally given as minus Laplacian plus potential plus alpha coefficients times delta distribution supported on the hypersurface C. And if you make it in a more rigorous way, you do this via transmission conditions. So you see here boundary conditions for the Schrödinger operator minus Laplacian plus V, which give you continuity. This is the top line in the boundary conditions of the traces, but the Neumann traces or the normal derivatives actually have a jump. There is some issues about operator domain regularity, but I do not want to go into details here. So one can just show that this A delta alpha is actually a self-adjoint operator. It's a semi-bounded. It is the proper definition or the right definition for the formal expression with the delta distribution. If you set alpha equal to 0, this reduces to the unperturbed operator, and also the spectrum of A delta alpha from a qualitative point of view, if the potential V is absent, is well understood. In that case, it would be the positive half line, and there's just finitely many discrete eigenvalues on the negative half line. Well, a long number of contributors in this context. Let me mention Pavel, who has been studying this for many decades and has made significant contributions to the understanding of such singular potentials in mathematical physics. And I would also like to mention a paper by Langerol, Lotorajczyk, and myself, where this was somehow viewed from an extension theory point of view, and which is kind of an inspiration for what you will be seeing now. So we need the spectral shift, and for that certain Weyl functions will appear, as you may guess. So again, we will be using Dirichlet-to-Neumann maps corresponding to the interior and the exterior domain. You take the sum of the two and the inverse, which is a function E of lambda that is well defined of the real line. Now again, we need conditions on the resolvent powers, which here is K being larger or equal to space dimension -3/4. That ensure that actually the 2K plus first power resolvent difference is trace class. It leads to a representation of the spectral shift function, which has some analogies to our first example, which was the Robin boundary conditions, in the sense that we need to work with this function script E on top. We need to modify it and build function script M0 and M1. M lambda and M naught, sorry, that you can see in the formula for the spectral shift, where again there is a certain constant appearing that serves as an upper bound for the strength coefficient in front of the distribution. Well, in space dimension 2 and 3, the condition for K is naturally satisfied with K being equal to 0, and the whole thing simplifies, and you get trace class for the resolvent difference and not just the higher power resolvent difference, and the corresponding formula for the spectral shift. So what I have been showing you is published not so long time ago in 2 papers with Fritz Gestegi and Shu Nakamura, as mentioned before. Particular emphasis is maybe the first paper, spectral shift functions and Dirichlet-Neumann maps, where the abstract machinery has been developed, and well, these applications that you have seen here are provided. So at that point, I would like to stop, and thank you very much for your attention.
Thank you very much. Any questions, please?
May I ask?
Yes, yes.
That's Grigory Rosenblum.
Nice to hear and see you here.
The same. Well, I wanted to make some remarks concerning your examples 1, 2, and 3.
Yes,
you
please.
See, there is a yes, exactly. There is a paper by myself. It is on the archive. It appeared somewhere in the end of May. Where
I know.
Yes, where I have considered this problem concerning the spectral properties, spectral estimates for the difference of resolvents or difference of power of resolvents, and there the results, for example, of trace class or something of the sort, appeared in much more singular situation. It's interesting for me. Have you seen how far these results of mine can be extended to some spectral shift function?
This is
Or probably they are too singular.
yeah. So of course I'm aware of these results, and you remember we spoke, or we talked a little bit about this paper via email. Well, I have not been trying to see if there is hope to get a representation for the spectral shift. What I have I'm a bit reluctant, let's say, now just by intuition. You see, the main technical difficulty here is to actually ensure the trace class property or the limit in trace class norm of a certain M function or Dirichlet-to-Neumann map. In the cases that you've been considering, if I remember right, these objects have less good analytic properties as well. So that would be the key issue, to ensure existence of limits to the real line. I'm not sure if it can be done. Maybe in certain cases, and it would indeed be actually very interesting.
So more questions?
Okay, thank you.
I have also a question. I mean, in the opposite direction than Grisha, who went to more singular. Looking at the third example with the delta on a hypersurface, I started wondering, because we know that such an operator can be approximated in a pretty good sense by regular Schrödinger operator with shrinking potentials. And so it came to my mind whether one can say something about how the scattering spectral shift function of the regular case converges to this.
Well, one would hope that this is actually true. I think Fritz has results in this direction, but the representation we have here is actually difficult to compare when you approximate delta with the sequence of scaled potentials. Because in that case, the shift for the approximating operators is actually constructed in a completely different way. The two objects,
I'm aware of that. Yeah, I'm well aware of
the two objects will be hard to actually compare them. But honestly, I have not tried. But I could imagine I could imagine difficulties here. But if I remember that, I think Fritz has a result in this direction: convergence of spectral shifts under convergence of but just classical potentials.
Okay. Yeah.
Yeah, I should look it up. I do not have it on my fingertips now.
Thanks.
So more questions?
Paper with
May I say a few
Roche
words
and
more?
Vickers. So I can send it to Pavel.
Yes. May I say a few, concerning the difference of powers of Laplace and Schrödinger, resolvents of Laplace and Schrödinger operators. I think it's proper to say that quite extensive results in this direction were obtained by Dima, whom we remember quite a lot of this conference paper. If I not, it was a great paper. It was a small paper by the size, but it was a great paper by the results, because he found conditions not necessarily for the potential having compact support or bounded. So under very general conditions, and even not for Laplacian, but for the polyharmonic operators. It's useful to remember Dima in this connection.
Yeah, thank you for this remark. Actually, this is very appropriate. Let's say example 2 would not work in this way for a non-compactly supported potential, right? Because the emphasis is here really on the splitting via a certain artificial boundary.
So more questions?
Yes.
So let us thank the speaker for a nice talk.
Thank you very much.
And so
Thank you.
Our session is over. Thank you for all, and see you tomorrow.
Well,
Tomorrow.
are there any questions or remarks or